Hello students, this is Dr. Krupa Rasane, Professor and Head ENC, Jain College of Engineering, Belgavi. This is the 10th video of our Module 4 in Power Electronics, BE 7th Semester ENC VTU. In this Module 4, we are basically dealing with the DC to DC converters or choppers, and the textbook that we are referring to is Mohammad H. Rashid, Power Electronic Circuits, Devices and Applications. In our earlier videos, we have looked into the DC to DC converter, the introduction, principle of step-down choppers, step-up choppers with R and RL load. Okay, and we have also seen the performance parameters in each of these circuits. And then we moved on to converter classification, where we have seen different types of converters with respect to the quadrantal operation. Then we saw special converters with respect to buck regulator, boost regulators. We have also seen the buck boost regulator, and in this video we would like to continue with the Cuk regulator. In the forthcoming videos, we'll be looking into the chopper circuit design. So these are the basic four classifications, that special type of DC to DC converters that we are looking at. So we'll be now concentrating on this Cuk converters, which basically has having two inductors and two capacitors connected in this fashion with a diode, okay, DM here. So we know that in buck chopper, energy only goes to the load when the switch is closed. So when I close the switch, energy goes to the load. That is your buck chopper. Next is in boost chopper, the energy only goes to the load when the switch will open. Then it will go to the load, right? Then in your buck boost converter as well as Cuk converter, the energy is transferred only when the switch is open and when it closes. That is for Cuk converter. Okay. So this was what we did, the classification. Looking at the Cuk converter, which is pronounced as Cuk, is a type of DC to DC converter that has an output voltage magnitude that is either greater than or less than the input voltage magnitude, very similar to buck boost converter. Okay, it is essentially a boost converter followed by a buck converter with a capacitor to couple the energy. So in the Cuk regulators, the circuit arrangement uses a power bipolar junction transistor as a switch. We'll be showing in the next slide. Similarly to the buck boost regulator, the Cuk regulator provides an output voltage that is less than or greater than the input voltage, but the output voltage polarity is opposite to that of the input voltage. Hence, it is also called as an inverter. It is named after its inventor. Cuk regulator, if you see the circuit diagram, it has, as I said, there are two inductors, one at the input, one here connected near the load end. There are capacitors C1 and C2. Okay, and this particular switch is in parallel with the supply. So basically we have got two types of switches. One is a switch which is controlled by the gate, and another switch which is an uncontrolled switch. And I can represent this in a switch representation format, where I will convert these two switches as a two mechanical switches with mode 1 and mode 2 operation. So when the input voltage is turned on, when I turn on and this transistor is switched off, then the diode DM is forward biased by the polarity of these capacitors, and the capacitor C1 is charged through this inductor L1. Okay, through this inductor L1, DM DM and the input supply Vs. The transistor Q1 acts as a controlled switch and the diode DM acts as an uncontrolled switch. They operate as two SPDT, single pole, single through current bidirectional switches. The circuit in figure A is often represented by these two switches as shown in figure B. So let us see how it works. The circuit operation can be divided into two modes of operation. So this is the switch representation. This is the mode 1 where the switch is put into this position, that is 1, or this is when the transistor Q1 is turned on at t equal to 0, and the current through the inductor L1 will rise in this fashion. So you see this is mode 1, transistor is switched on, so the circuit will look like this, right? So this gets short circuited and you will get the current that is rising through the inductor L1 at t equal to 0. At the same time, the voltage of the capacitor C1, see the C1 is there, though your DM is open circuit, C1 is in picture, L is in picture, and this capacitor and load R is still in picture. So at this time, the voltage of this capacitor C1 will reverse bias DM and turn it off. So the DM gets off and your transistor Q1 gets turned on. The capacitor C1 discharges its energy to the circuit formed by C1, okay, C2, the load also, and L2. So this is how the operation in mode 1 is. L1 will be charging directly connected to Vs and current will increase and charge this L1. And at the same time C1 gets connected to L2 and this C2 and the load, and the capacitor which is charged earlier, right, it will discharge through its energy through the circuit that is formed by C1, C2, the load as well, and also the L2. So in the mode 2, so this is the diagram in mode 2. It begins when the transistor is turned off. So now the transistor is turned off at t equal to T1 and diode gets forward biased. The capacitor C1, which is discharged from the input, now gets connected to the supply. So this capacitor, because your transistor now is open, right, this path gets opened and this path gets closed, so capacitor automatically gets connected to the supply. So the capacitor C1 is charged, so it will start to charge from the input supply and the energy stored in L2. This is one path, and L2, this is another path, okay, and the energy that is stored in L2 is transferred to the load. So this is how it will also transfer the energy stored in L2 to through this capacitor, this is a closed loop, and to the load as well. Okay, so this is how your mode 2 operation occurs. The diode DM and transistor Q1 provide a synchronous switching action. So you see when it switches this side, who is supplying the load current? Your C1 is supplying, and in mode 2 who is supplying? The L2 will be supplying the load current. So for both the switching operation, the load current will be getting the current. The capacitor C1 is the medium for transferring energy from the source to load. Since it is connected in series with the load as well as to the load, the capacitor C1 is the medium for transferring energy from the source to the load. The equivalent circuit for the modes are shown above, and the waveforms I'll be showing in the next slide for a continuous load current. So this is the waveform for a continuous load current. This is the voltage across the thyristor. VT means the switch, the main switch that is connected here. And during 0 to T on, when the transistor is on, right, the voltage across the transistor or VT is going to be 0 because it is acting like a switch on. And during switch off, the transistor will open up, right, and hence the voltage across the transistor will be equal to Vs minus the voltage drop across the inductor. So it is Vs minus L1 into di by dt. That is the voltage that is going to come across this when it is off. Now coming to the next diagram, this is your VDM, that is another switch. We call it as uncontrolled switch. During the turn on period, right, during the turn on period, it is basically subjected to DM is going to be off. and it is off with the polarity of Vc1. So it is going to be having a voltage of minus VDM, right? So you have to take a reverse voltage because it is off, and it will be subjected to the voltage across this capacitor. Fine. So as long as it is on and off, when it is on during the off period, it is going to turn on, right? So then the voltage across the diode is going to be 0. So we know that whenever a switch is on, the voltage across it is going to be 0. And whenever it is off, it is going to have a voltage which is across it. The circuit voltage that comes across it. Now this is your current waveform for L1 inductor. During the on period, the inductor current for L1 is going to rise from a minimum value of IL11 to IL12. Okay, and the average value of this current is going to be the supply current IS, average value of input. Okay, and that is going to be what across the current going through the inductor. So this inductor will have a rising current going from IL11 to IL12, and again it will fall to IL1 during the off period, and the average value between these two will be IS, and the ripple current that comes across this inductor, because VL is equal to di by dt. So di by dt is the change of current, that is delta I1. That will be the ripple current, that is difference between this value and this value. Similarly, we have one more inductor IL2, which basically is also charging in mode 1. In mode 1, the capacitor is the one which is going to discharge through the load at the inductor L2. During that time, it is seen that the current rises from IL21 to IL22. Okay, and average value of this is equivalent to the load current, that is inductor current IL2, I would say. Okay, so IL2 will be the average value, and delta I2 will be the ripple current that is going to flow through this L2. The next waveform is the capacitor voltage IC2. So IC2 is this capacitor during the mode 1. You know that C1 is discharging through this, right? So you will see that the current through the capacitor is shown in this direction. So it will be in the positive. So for the capacitor IC2, it is going to be initially from negative, right? Then it will rise and reach the positive. So it is the same current that is flowing through the inductor and through the capacitor C1 as well. Okay, but you will note that IC2 will have both polarities, positive and negative. That is because of the capacitor and inductor coming in series. So we will have the average, because this capacitor is only going to carry the ripple. It will not carry the average current. So whatever is this ripple, it will going to flow through this IC2. Okay. Next, and its average value will be 0. Current value. Next is the ripple voltage across this capacitor Vc2. So it will always develop a ripple voltage, right? It will develop a ripple voltage, and that ripple voltage will be from minimum to maximum value, right? And it is called as the ripple voltage Vc2, and its average value is going to be the DC voltage that is coming across the load, because it is in parallel with the capacitor. So this load is going to be the same voltage that is going to be, and since we are saying that the load, this will be filtered and only DC is going to come here, the DC value of the load is VA. That's how I call it, and it is in our Cuk case, it is inverted of the input. So we write it as minus VA, and I get a rippling effect across the capacitor. So that is your delta VCT, that is the filtering effect. Okay. Next is IC1. So IC1, as you know, during the on time, it is going to be in the discharging fashion with this polarity shown. right? So with this polarity, it means that the inductor L2 IC1 is going to be discharging through this inductor and capacitor. So we can say that it is rising from here to here. The polarity needs to be looked at. And during the off time, this capacitor is going to be charged by the capacitor. Now the polarity of the IC1 has to be in this fashion because it is going to be charged. Hence you will see a negative downward position, and from here it will look negative and it will start to rise and charge. So the polarity of the IC1 will appear inverted in the waveform because when it gets connected to Vs, it is in the charging position connected to Vs. So it will have it in this fashion and it will become plus minus, okay, at the end. And this will continue, and the load, we are saying that the load current, come what may, for both on and off time, it is going to carry a DC current of IA. Now in the Cuk regulator, let us assume that the current in the inductor L1, so this is your inductor L1, it rises linearly from IL1 1 to IL1 2, okay, and this time period is T1. So we are assuming that, and then because of that, during this period, what is on? Your transistor is on. So the circuit that is in existence is this particular circuit. So what is the voltage across the inductor? Is nothing but only Vs, because this is on. So this voltage is 0. So we'll get the equation Vs is equal to L into di by dt, and di by dt means we know the change in current from IL11 to IL12, and divided by dt, time taken is t1. So with this I get the expression L1 di1 by t1, okay. Or I can take the t1 on the left hand side and I will get delta I1 into L1, okay, divided by Vs, that is t1. And due to the charged capacitor C1, the current of inductor L1 falls linearly from L112 to L111 during the off period. That is when this transistor opens up. Okay, what is the inductor value? It is nothing but this is open, so it is voltage at this point and voltage at this point. At this point it is Vs, and at this point this is going to be on, so it is nothing but the voltage across the capacitor. So you will get the inductor voltage across would be Vs minus Vc1. That is equal to, because the current is falling, slope is falling, we'll get minus L1 delta I1 by T2 during the period of T2. Taking T2 on the left hand side, I will get delta I1 into L1 divided by Vs minus Vc1. Okay, where Vc1 is what? Vc1 is the average voltage across the capacitor C1, and delta I1 is the ripple current through the inductor L1, which is equal to IL12 minus IL11. Now with this I can take delta I1 on the left hand side. So that is BC. You can see here I have got delta I1, here I have got delta I1. Okay, so I'll take for both and equate it together. So delta I1 becomes Vs into T1 by L1. So this will become equal to, take delta I1 here, so V minus of Vs minus Vc1 into T2 divided by L1. So when I equate it like this, right? So this is what I have done. Now I will substitute T1 is equal to KT. We know it is on time, which is equal to K times capital T, where capital T is the chopping frequency and T2 is the off time and is equal to your off time, which is equal to 1 minus K into T. Okay, so substituting these two in this particular equation, I will be getting an expression for the average voltage of the capacitor C1, which will be equal to Vc1 will be equal to Vs upon 1 minus K. Okay, so assuming that the current of filter L2, now let us look at the other inductor, that is L2. Now for L2 also, the current during the on time, that is the mode 1, it is charging from L2 1 to L2 2. Okay, so assuming that the current of filter inductor L2 rises from IL21 to IL22 in time period T1, then during that time, what is the voltage? This is off. So the voltage at this point will be VC1 and at this point will be VA. So VA is a load voltage, right? So VC1, and this is a negative, here is plus and here is minus. So it will be VC1 plus VC2. These two will add up. So this will be equal to L2 into di by dt. So di is nothing but ILT2 minus IL21 upon T1. That is equal to L2 into delta I2 by T1. Take T1 on the left hand side. I will get delta I2 into L2 divided by VC1 plus VA. If I take delta I2 on the left hand side, I will get VC1 plus VA into T1 by T2. And the current of the inductor L2 during T2 is going to fall from L2 to L2 in the time period that is T2. Okay, so when during that time this is going to be on. So what is this is 0. This point is 0 voltage across the inductor L2. This point is 0. This is on, and this point is nothing but VA. So that time VA is equal to, since the current is falling, it will be minus L2 into delta I2 by T2. Taking T2 on the left hand side, I will get minus delta I2 into L2 divided by VA, or taking delta I2 on the left hand side, I will get VA into T2 by L2. So you can note that here also I have got delta I2 in terms of T1, I have got delta I2 in terms of T2. I can equate both of them since they are equal to delta. Okay, so this is exactly what we are doing now. Both the I2s we will equate together. Okay, and after equating I get this particular expression, and then I will substitute T1 and T2 as I did for L1. After substituting, I'll get the average capacitor value for C1 again. So C1, in this case, I'll get minus VA upon K. And we know that earlier we got VC1 as equal to Vs upon 1 minus K with respect to L1. Now both are VC1, both are average voltage across the capacitor C1. Let us equate to them, and we will get VA is equal to K into Vs upon 1 minus K, or K becomes equal to VA upon VA minus VK. Just play with this and you will substitute this value and you will be getting VA equal to K into Vs upon 1 minus AK. Note that VA is the output DC voltage, Vs is the input, and K is the duty cycle of the chopping frequency, which is equal to T on upon capital T. So now let us move ahead with peak-to-peak ripple currents of inductors. So the switching period is capital T, and it can be found where T is equal to 1 by F, which is nothing but summation of T1 plus T2. We know that T1 is equal to delta I1 L by Vs, and T2 is minus delta I1 L upon Vs minus Vc1. So we will just, this is minus, so we will be this minus of this, right? So we will get, take LCM, Vs into Vs minus Vc1, and we will be getting this particular expression. And this will give me an expression for delta I1, which is equal to minus Vs into Vs minus Vc1 divided by this F into L, right? F into L1. So the switching period T can also be found by taking T1 plus T2, which is equal to delta I2. This was in terms of delta I1 and this is in terms of delta I2. Okay, take both the T1 plus T2 in terms of delta I2. I get an expression in this fashion, and this will also give me a ripple current for delta I2. Okay, so I get an expression for delta I2, which is equal to minus of VA into 1 minus K upon FL2, and this, if I solve, will be equal to K into Vs upon F into L2. Okay, we have substituted the known parameters for VA into 1 minus K as K into Vs. So this is how we get the expression for delta I1 and delta I2. Coming to peak ripple voltages of capacitor, when the transistor Q1 is off, the energy transfer capacitor C1 is charged by the input current for the time period T equal to T2. The average charging current of C1 is IC1, which is equal to IS, and the peak-to-peak ripple voltage of the capacitor C1 is given by Vc1. We know the voltage across a capacitor is 1 upon C integration into the current equation. So IC1 into dt from 0 to T2. So substituting 1 upon C1, 0 to T, this IC1 is nothing but the input current IS into dt. So this comes out as IS into T2 upon T1. So we know that T2 is equal to Vs upon Vs minus Va into F, and substituting in the above we get this equation which will become delta Vc1 is equal to Is into Vs upon Vs minus Va into F upon this C1, or delta C1 becomes equal to Is into 1 minus K upon Fc1. We have substituted for Vs into divided by Vs minus Va, which is equal to 1 minus K. So if we assume that the load current load ripple current delta I0 is negligible, then delta L2, that is change in the current in inductor L2 is equal to the change in the current in the capacitor C2. So we are assuming this. The average charging current of C2, which flows for time T by 2, is IC2 equal to delta I2 by 4. This is, we have to analyze this ourselves, and the peak to peak ripple voltage can be got as delta Vc2 is equal to 1 upon C2, 0 to T2, T by 2 half the time. IC2 into dt is equal to 1 upon C2. Okay, and we are substituting IC2 is equal to delta I2 by 4 into dt, which is equal to delta I2 upon 8 FC2. And if you solve this, I'll be getting an expression for delta C2 equal to VA into delta I2. I am substituting as VA into 1 minus K upon 8 C2L F squared. Now this can be rewritten as K into Vs upon 8 C2L2 F squared, because we know that VA into 1 minus K is K into Vs. So now let us look at the condition for continuous inductor current and capacitor voltage. If IL1 is the average current of the inductor L1, the inductor ripple current delta I1 is equal to 2 times the IL1. Okay, so we are considering this as I1 and it will reach to the same value. So this will be 2 times, and which is equal to Is as well. So we know that Is is equal to K into Ia upon 1 minus K, and delta I1 is equal to Vs into K upon F into L1. We have derived it in previous slides. So using these equations, I will equate delta I equal, that is KVS upon FL1 is equal to delta I1 is equal to 2 times IL1, which is equal to 2 times Is, and hence this becomes equal to Is is equal to KIA upon 1 minus K. So this is equal to 2 into Ia can be written as Vs upon R, VA upon R, and VA is equal to, we know the value of VA, which is equal to K into Vs upon 1 minus K. So when I substitute for Ia equal to VA by R and VA equal to KVS upon 1 minus K, the right hand side term becomes equal to 2 into K upon 1 minus K, the whole squared into Vs by R. This gives the critical value of the inductor LC1. Okay, that is L1, which is equal to 1 in this, if you see, Vs and Vs cancels and 1k cancels. So you will get 1 minus k into R the whole squared divided by 2k, this 2 into k, this k, and F will be there remaining. Okay, so this becomes a critical value of inductor, and this is the value which is the required condition for continuous inductor current. Now let us look at the capacitor. We'll use the same equation. Delta I2 is equal to K into Vs upon F into L2. This also we have derived earlier. And using these equations, we'll be getting 2 times IL2 will be treated as this is nothing but 2 times IL2. Average value of inductor current IL2 is same as the load current, that is IA. So this will be equal to KVS upon FL2 equal to 2 IL2, which is equal to 2 into the load current IA. So this can be equated to 2 into IA is VA by R, which is equal to 2 into KVS upon 1 minus R into 1 minus K into R. This gives a critical value of the inductor LC2, which is equal to L2 becomes equal to 1 minus K into R. K cancels, right? And Vs also cancels. So you'll be remain with 1 minus K into R upon 2F. This 2 and F. So this is the critical value of the inductor, critical value of the inductor L2. Okay. A continuous ripple current. Now, let us move forward with the example problem, that is finding the currents and voltages in the Cuk regulator. So this is the circuit diagram given to us. The input voltage of a Cuk converter is given here in this figure, and it has an input voltage of 12 volts. The duty cycle K is given as 0.25 and the switching frequency is 25 kilohertz. The filter inductance is L2 is 150 microhenries and filter capacitance C2 is C2 is 220 microfarads. The energy transfer capacitance of C1 is 200 microfarads, and the inductance L1 is equal to 180 microhenries. So the average load current is IA is 1.25 amperes. You are supposed to determine the average output voltage VA, the average input current IS, the peak to peak ripple current of inductor L1, that is delta I1, and peak to peak ripple voltage of capacitor C1, that is delta VC1, the peak to peak ripple current of inductor L2, that is delta I2, and F is the peak to peak ripple voltage of capacitor C2, delta VC2, and the peak current of the transistor IP. So these values you'll have to determine. Now coming to the solution, we know that Vs is equal to 12 volts given parameters. K is equal to 0.25. The load current IA is 1.25 amperes. The frequency or chopping frequency is 25 kilohertz. The inductance value is 180 microhenry. The capacitance value is 200 microfarads. The inductance value L2 is 150 microhenry, and the capacitance C2 equal to 220 microfarads. So in the first case, they have asked you to find the load voltage VA. For that, I will use this formula. VA is equal to minus of K into Vs upon 1 minus K. After substituting K as 0.25 and K as 0.25 and input voltage as 12 volts divided by 1 minus of 0.25. Okay, so I'll be getting equal to minus 4 volts. Similarly, for this part B of this problem, we know that Is is equal to K into Ia upon 1 minus K. So I'll be getting 1.25, that is Ia, they have given Ia as 1.25 into K is 0.25 divided by 1 minus 0.25, and this will give me as 0.242 amperes. Note that the input voltage was 12 volts, I got 4 amperes. Input current now I am getting as equal to 0.42 amperes. Now the ripple current I1 is delta I1 is equal to Vs into K upon F into L1. So substituting the values of Vs as 12, K as 0.25 divided by frequencies given as 25 kilohertz, and L1 value is given as 180 into 10 to the power of minus 6 microhenries. So I'll be getting the ripple current as 0.67 amperes. Next, to evaluate the ripple voltage across C1, delta VC1, we know the formula is equal to Is into 1 minus K upon FC1. So substituting the value of Is, I have got it as 0.42 into 1 minus 0.25 divided by frequency is 25 kilohertz multiplied by C1. C1 value is 200 microfarads, and that will give me the delta VC1 as 63 millivolts. Next, looking into your this you're supposed to find the ripple current delta I2 equal to KVS upon FL2. Substituting the values, I'll be getting the answer delta I2 equal to 0.8 amperes. Next, we have to find delta VC2. Delta VC2 is equal to delta I2 upon 8FC2. These are the formulas we have derived in earlier slides. So delta I2 we have just derived, delta I2 is equal to 0.8 we have just derived from E, and that divided by 8F into C2. C2 is 220 microfarads, and that will give me 18.18 millivolts. Continuing with the example problem, for the part G, the average voltage of across the diode is asked. This can be found by VDM equal to minus KVC1 equal to minus VAK upon 1 upon, okay, I'm just substituting it. So this will give me voltage across VDM is equal to VA. Now for a lossless circuit, the current IL2 into the flowing through VDM, okay, that is power across VDM is equal to power across the load. And the average value of the current in the inductor L2, IL2 is equal to I into VA upon VDM. So when I take this IL2 on the left hand side, I'll be getting VA IA upon VDM, and this is same as IA. Okay, so these two cancels and I will be getting it as 0.25 because VDM we have calculated it as VA. Therefore, the peak current of transistor I peak is equal to the input current Is plus the delta I1 by 2 plus current through the inductor L2 plus the ripple current I2 upon 2. So if I add all this, that should give me the peak value. So Is is we know is 0.42 plus 0.67 by 2 we have evaluated in the previous slide, and IL2 is 1.25 and delta I2 by 2 is 0.8 by 2. So this should give me the value of 2.405 amperes. This is the peak value of the ripple current. So in this particular video, we have looked deeply into Cuk regulator. We have evaluated the parameter values, okay, the components that are used. And we have also looked into the critical values of the components of L1, L2, C1 and C2 for continuous load current. This was followed by an example problem that we have solved. So with this, we'll complete this particular video. And I thank you for your patient listening and hope if you have any doubts, any questions, do get back to me. Thank you so much.